There's a star so close we can see it with nothing but our eyes, a system burning just 4 light years away, near enough that every civilization on Earth has mapped it, named it, woven stories around it. For generations, we believed proximity meant possibility. We thought nearness was the same as access. And then James Webb turned its instruments toward Alpha Centauri, not in triumph, but in careful scrutiny. And what came back wasn't the confirmation scientists had quietly hoped for. It was something harder to interpret, something that asked more questions than it answered. The data didn't reveal life or worlds ready for exploration. It revealed limits. And those limits changed everything. If this journey interests you, you can subscribe and follow along as we search for the quiet clues the universe leaves behind. The first thing you need to understand about Alpha Centauri is that it's been lying to us through proximity. Not intentionally, of course. Stars don't deceive, but human psychology does. We see something close and we assume it's within reach. We measure distance in light years and think 4 sounds manageable, almost trivial compared to the thousands and millions that separate us from everything else out there. 4 light years. The kind of number you can say out loud without stumbling. The kind of distance that feels, irrationally, like it might be crossable in a lifetime. And for decades, that nearness shaped how we thought about Alpha Centauri, how we wrote about it, how we dreamed about it. But 4 light years is not a distance, it's a gulf. To understand what James Webb saw when it looked toward Alpha Centauri, you first have to understand what Alpha Centauri actually is, and why it occupies such a strange place in our collective imagination. Most people think of it as a single star, the closest one to our Sun. That's technically correct, but meaningfully incomplete. Alpha Centauri isn't 1 star, it's 3. A triple system locked in gravitational choreography, orbiting a common center of mass in a dance that's been unfolding for billions of years. There's Alpha Centauri A, a star slightly larger and brighter than our Sun. There's Alpha Centauri B, slightly smaller and dimmer. And then farther out, moving in a wide, slow orbit around the pair, there's Proxima Centauri, a red dwarf so faint you need a telescope just to confirm it exists. These 3 stars sit in the southern sky, visible from anywhere below the equator, bright enough that ancient peoples tracked them, used them for navigation, gave them names that meant the foot or the pointer, depending on the culture doing the naming. To observers in the southern hemisphere, Alpha Centauri is as familiar as Polaris is to the north. It's part of the horizon, part of the night, part of the world, and that familiarity breeds something dangerous in science: assumption. For a long time, we assumed that a system this close would be easy to study. We assumed that nearness would translate into clarity. We assumed that if we built instruments powerful enough, sensitive enough, we could simply look at Alpha Centauri and see what was there: planets, atmospheres, chemistry, maybe even signatures that hinted at something more. The logic seemed bulletproof. If we can see distant galaxies, if we can peer into star-forming regions thousands of light years away, then surely a star system sitting practically in our backyard would be simple to decode. James Webb was supposed to make that true. When the telescope launched in December 2021, when it traveled 1 million miles from Earth to its position at the second Lagrange point, when it unfurled its segmented golden mirror and began cooling its instruments to temperatures barely above absolute zero, the astronomy community held its breath. Webb wasn't designed for any one target. It was designed to see everything we'd been missing: galaxies at the edge of time, exoplanet atmospheres, star birth, molecular clouds, the infrared universe in all its hidden detail. But among the thousands of potential targets, among all the distant wonders Webb could observe, Alpha Centauri held a special place. Because it was close, because it mattered, because if there was anywhere we might one day send a probe, a mission, even a signal, it would be there. So scientists proposed observations. They designed programs. They requested time on Webb's crowded schedule. And eventually, the telescope turned toward Alpha Centauri, not with fanfare, not with press releases, but with the quiet, methodical precision that defines modern astronomy. The instruments activated. Photons that had traveled 4 years through the void entered the mirrors, bounced through the optics, and landed on detectors chilled to just a few degrees above absolute zero. Data began to accumulate, and slowly, carefully, scientists began to look at what Webb had actually seen. What came back wasn't what anyone expected. There's a particular kind of disappointment in astronomy that doesn't come from failure. It comes from clarity, from seeing exactly what's there and realizing it doesn't match the story you'd been telling yourself. James Webb didn't fail when it observed Alpha Centauri. It succeeded completely. The data was clean, precise, exactly what the instruments were designed to capture. The problem wasn't the telescope, the problem was reality. Let's start with what Webb actually sees when it looks at a star. Most people imagine telescopes as cameras that simply take pictures, that point at an object and capture it the way a photographer captures a landscape. But Webb doesn't work like that. It doesn't see invisible light, the wavelengths human eyes detect. It sees in infrared the realm of heat, of warm objects glowing invisibly in the dark. Everything in the universe emits infrared radiation: stars, planets, dust, gas, even the telescope itself, which is why Webb has to be so cold, why every component is chilled and shielded to prevent its own heat from contaminating the signal. When Webb looks at Alpha Centauri, it's not just seeing stars, it's seeing heat signatures, thermal emissions, the glow of objects warmed by starlight, and in a system with 3 stars all radiating energy, all heating everything around them, the infrared landscape becomes complicated very quickly. There's light from the stars themselves, of course overwhelmingly bright, flooding the detectors. But Webb's designers anticipated that. They built coronagraphs, instruments that block out the direct light from a star so the telescope can see what's nearby: planets, disks, the faint infrared whispers that might indicate something orbiting in the shadows. Scientists used those coronagraphs when they pointed Webb at Alpha Centauri. They blocked the light from Alpha Centauri A and B, masked the overwhelming glare, and looked at what remained. And what remained was dust. Dust sounds mundane. It sounds like something you'd find under furniture, an annoyance, a thing to be cleaned away. But in astronomy, dust is a messenger. It tells you where matter exists, how it's distributed, what temperatures it reaches, whether it's clumped into structures or spread diffusely through space. Dust absorbs starlight and re-emits it as infrared. It glows, and Webb is exquisitely sensitive to that glow. When the telescope looked at Alpha Centauri, it saw dust scattered through the system, grains of silicate and carbon warmed by the stars, radiating heat in patterns that revealed their locations, their densities, their sizes. The dust was there. That wasn't a surprise. Every star system has dust. Our own solar system is full of it, tiny particles orbiting the sun, remnants of collisions and comets, and the slow grinding of rocks against each other over billions of years. What surprised scientists wasn't the presence of dust around Alpha Centauri. It was the configuration, the temperature, the unexpected distribution that didn't quite fit the models. In theoretical models, dust in a multi-star system should behave in predictable ways. Gravitational interactions between the stars should clear out certain regions, sweep particles into stable zones, create gaps and rings and structures that follow mathematical rules. Scientists had run simulations of Alpha Centauri for years, modeling how dust should distribute itself around 3 stars in that particular configuration. They expected to see certain patterns, certain gaps, certain concentrations. What Webb saw didn't match. There was dust where the models said there should be less. There were thermal signatures at temperatures that didn't align with predictions. And more troubling, there were absences, regions where scientists expected to see warm dust, where planets forming or migrating should have left traces, showed nothing, or almost nothing. Signals so faint they barely rose above the noise floor, so ambiguous they could be interpreted 6 ways. This is where the shock came in, not from discovery, but from confusion, from data that refused to confirm or deny what scientists had expected. In astronomy, there are good surprises and bad surprises. Good surprises are when you find something unexpected but interpretable, something that challenges theory, but offers a clear path forward. Bad surprises are when the data just doesn't make sense, when it sits there defying explanation, when every interpretation you try seems incomplete or forced. The dust around Alpha Centauri was a bad surprise. Scientists began analyzing the thermal emissions, trying to match the infrared signatures to physical models. Dust grains come in different sizes, different compositions, and each combination radiates heat differently. By measuring the spectrum of infrared light, by looking at which wavelengths were bright and which were dim, researchers could in principle determine what kind of dust they were seeing, how large the particles were, how far from the stars they orbited. The data was good enough for that analysis. Webb's instruments had the resolution, the sensitivity, the calibration, but the results kept coming back strange. Some of the dust appeared to be warmer than it should be for its distance from the stars. Other dust seemed too cool, as if something was shading it, blocking some of the starlight that should have been heating it. There were hints of clumping, concentrations of material that might indicate planets shepherding dust into resonant orbits, but the patterns weren't clear enough to confirm. And underlying everything was a persistent question: if there were planets in the habitable zones of Alpha Centauri A or B, planets warm enough for liquid water, wouldn't they leave clearer traces in the dust distribution? Wouldn't their gravity sculpt the surrounding material into recognizable structures? Webb looked, it measured, it captured every photon it could, and the answer it gave was maybe, or maybe not, or maybe the question itself was wrong. Here's what most people don't understand about observing exoplanets. Finding a planet is not the same as seeing a planet. When astronomers say they've discovered a planet around another star, they usually mean they've detected an indirect effect. A wobble in the star's motion caused by a planet's gravity, a dimming of starlight as a planet crosses in front of the star, a gap in a dust disk that suggests a planet has cleared a path through the material. Direct imaging, actually capturing photons reflected or emitted by the planet itself, is incredibly rare and usually only possible for very large planets orbiting very far from very young stars, objects that are still hot from formation, still glowing brightly enough in infrared to be distinguished from their stars. For a planet like Earth, orbiting a sun, like star at Earth, like distances, direct imaging is effectively impossible with current technology. Even with Webb, even with Alpha Centauri being 4 light years away instead of 400, the problem is brightness ratio. A star like Alpha Centauri A emits roughly 1 billion times more light than an Earth-like planet would reflect. In visible light, that planet would be 1 billion times fainter than the star. In infrared, the ratio improves slightly because planets emit their own heat, but it's still overwhelming. It's like trying to see a candle next to a searchlight. The coronagraph helps, blocking out the searchlight so you can look for the candle. But even with the star blocked, you're looking for something unimaginably faint. A signal buried in noise, scattered light, residual glare from the star, cosmic rays hitting the detector, thermal fluctuations in the telescope itself. Webb's coronagraphs are good. They're the best ever built for infrared astronomy. But they're not perfect. They reduce the starlight by a factor of 10,000, maybe 100,000, depending on the configuration. That's not enough to see an Earth, not directly, not as a clear, distinct point of light. What you can do, what scientists tried to do with the Alpha Centauri observations, is look for statistical anomalies, asymmetries in the scattered light, warm spots that don't align with dust models, anything that might indicate a planet's presence even if the planet itself remains invisible. The data showed asymmetries. The data showed warm spots, but the data also showed noise, and separating signal from noise, real features from instrumental artifacts, proved harder than anyone wanted to admit. One team analyzing the observations thought they saw evidence of a warm object in the habitable zone of Alpha Centauri A. The thermal signature was faint but persistent, appearing in multiple wavelength channels, sitting at roughly the right distance for liquid water to exist on a rocky surface. They ran statistical tests, checked for instrumental effects, compared the signal to simulations of what a planet should look like. The results were tantalizing but not definitive. The signal could be a planet, or it could be a clump of dust, or it could be a background star, unrelated to Alpha Centauri, that happened to fall along the same line of sight and wasn't fully removed during data processing. Another team looked at the same data and saw nothing. They argued that the signal the first team identified was within the noise margin, that it disappeared when you applied different data reduction techniques, that it was more likely a statistical fluctuation than a real object. They weren't dismissing the possibility of planets. They were pointing out that the evidence wasn't strong enough to claim a detection. And this is where the shock deepened, not because Webb failed to find planets, but because it revealed how little we can actually see, even when we're looking at the closest stars with the most powerful telescope ever built. The expectation, the quiet hope, had been that proximity would translate into certainty, that at 4 light years, with Webb's capabilities, we'd finally get clear answers about what exists in the Alpha Centauri system, planets or no planets, habitable zones occupied or empty, chemistry that hints at life or chemistry that's sterile and dead. Instead, we got ambiguity, we got constraints, we got better limits on what could exist, but not confirmation of what does. Scientists are now fairly confident that there are no large planets, nothing Jupiter-sized or even Neptune-sized, orbiting close to Alpha Centauri A or B. If those planets existed, Webb would have seen them. The data rules them out. There are also no massive dust disks, no thick clouds of material like the ones we see around young stars still forming planetary systems. Alpha Centauri is old, several billion years old, and most of its primordial dust has either accreted into planets or been blown away by stellar winds. What remains is a thin haze, the equivalent of the zodiacal dust in our solar system, difficult to see and even more difficult to interpret. But small planets, Earth-sized or smaller, rocky worlds orbiting in the temperate zones where water could remain liquid, those remain possible. The data doesn't confirm them. It doesn't rule them out either. They exist in a space of uncertainty, allowed by the observations but not required by them. And that uncertainty is maddening because Alpha Centauri is right there, close enough to study, close enough to imagine visiting, but still too far to truly know. Let's talk about what too far actually means. For light, years sounds small in cosmic terms, and it is, in a universe measured in billions of light years, where galaxies sit millions and billions of light years apart, where the observable universe stretches 46 billion light years in every direction. 4 light years is effectively 0. It's the next room, the next house, practically touching. But in human terms, in terms of travel, of reaching something with a machine we build and launch, 4 light years is an eternity. Light moves at 300,000 kilometers per second, the fastest speed anything can travel according to our understanding of physics. At that speed, light from Alpha Centauri takes just over 4 years to reach Earth. 4 years sounds manageable. Voyager 1, the most distant human-made object, launched in 1977 and has been traveling ever since, is currently about 22 light hours from Earth. In 45 years, it's covered 22 light hours. At its current speed, it would take Voyager 1 roughly 70,000 years to reach Alpha Centauri. 70,000 years, longer than recorded human history, longer than our species has had language, agriculture, cities. There are proposals for faster spacecraft. Breakthrough Starshot, an initiative funded by billionaire Yuri Milner and backed by scientists including Stephen Hawking before his death, envisions tiny probes accelerated by powerful lasers to 20% the speed of light. At that speed, a probe could reach Alpha Centauri in about 20 years. But the engineering challenges are immense. The probes would need to be incredibly small, just grams in mass, to accelerate that quickly. They'd need light sails that could withstand the intense laser energy without melting or tearing. They'd need electronics that could survive 20 years in interstellar space, bombarded by cosmic rays, with no possibility of repair. And even if you solved all those problems, even if you built and launched such a probe, you'd wait 20 years for it to arrive, and then another 4 years for its signals to return to Earth, a round-trip communication time of nearly 3 decades. That's the reality of close. Alpha Centauri is close by cosmic standards and unreachable by human ones. And that contradiction, that gap between nearness and access, defines our relationship with the system. It's why every new observation matters. Why every telescope pointed in that direction carries weight. Because if we can't go there, if we can't send humans or even sophisticated robots within any reasonable time frame, then understanding Alpha Centauri depends entirely on what we can see from here, on what our instruments can detect across 4 light years of empty space. James Webb gave us better eyes, but better eyes don't always mean clearer answers. The scientists analyzing Webb's Alpha Centauri observations published their initial findings in late 2023, about a year after the data was collected. The papers were careful, hedged with caveats, full of phrases like consistent with, and cannot rule out, and requires further observation. There were no press releases claiming discovery, no headlines announcing planets. Instead, the publications focused on what the data constrained, what it eliminated, what it made less likely. They presented thermal maps of the dust distribution, models of possible planetary configurations, estimates of detection limits for different planet sizes at different orbital distances. The tone was cautious, almost disappointed, and in the comment sections of astronomy forums, in the social media discussions among space enthusiasts, you could feel the frustration. People had expected more. They'd expected Webb to deliver clarity, to answer the question of whether Alpha Centauri hosts habitable planets. Instead, they got papers full of error bars and confidence intervals, careful statements about what might be there if you squint at the data in certain ways. But here's what those papers actually represented: progress. Not the satisfying kind, not the breakthrough that makes headlines, but the slow, grinding progress of science constraining reality. Before Webb's observations, the range of possible planetary systems around Alpha Centauri was enormous. There could be multiple Earth-sized planets. There could be none. There could be massive asteroid belts or quiet, empty spaces. The uncertainty was wide enough that almost any configuration seemed plausible. After Webb, that uncertainty narrowed, not to a point, not to a definitive answer, but to a smaller range of possibilities. Large planets, unlikely. Massive dust disk absent. Warm dust in unexpected locations, present and poorly explained. Small rocky planets in habitable zones, still possible, still undetected, still waiting for better observations or different techniques. That narrowing is how astronomy works. You don't typically point a telescope at something and immediately understand it. You point the telescope, collect data, analyze it, publish results, and then other scientists argue with you. They reanalyze the data using different methods. They propose alternative explanations. They design new observations to test competing hypotheses. Slowly, over years or decades, a consensus emerges. Or it doesn't, and the debate continues. But even ongoing debate is progress because it refines the questions, sharpens the arguments, eliminates the ideas that don't survive scrutiny. Webb's observations of Alpha Centauri sparked exactly that kind of scientific conversation. Teams around the world requested the raw data, applied their own processing pipelines, tested different interpretations. Some found signals others missed, some dismissed signals others thought significant. And through all of it, the picture of Alpha Centauri became slightly clearer. Not resolved, but less fuzzy, less open to wild speculation. One of the unexpected findings from the Webb data involved Alpha Centauri b, the slightly smaller companion to Alpha Centauri a. Previous observations from ground-based telescopes had suggested that Alpha Centauri b might have a planet, a roughly Earth-mass world orbiting very close to the star, too close to be habitable but interesting nonetheless. The detection was controversial, based on radial velocity measurements that showed a periodic wobble in the star's motion, the signature of a planet's gravitational tug. But the signal was weak, right at the edge of what the instruments could reliably detect, and some astronomers argued it was an artifact, a false positive caused by stellar activity or instrumental noise. Webb couldn't directly see a planet that close to Alpha Centauri b, but it could look for the planet's heat. An Earth-mass planet orbiting that close to a star would be scorching hot, hundreds of degrees, radiating strongly in infrared. If the planet existed, Webb should detect its thermal emission, even if it couldn't resolve the planet as a separate point of light. The telescope looked, the data came back, and there was no clear signal, no strong infrared excess at the location where the planet should be. The result wasn't definitive. The planet could still exist, but be cooler than expected, or oriented in its orbit such that Webb was seeing its night side, or surrounded by dust that absorbed its heat. But it was suggestive. It made the planet's existence less certain, more doubtful. The team that originally claimed the detection stood by their findings, arguing that radial velocity was a more direct measurement than infrared excess. But other scientists grew more skeptical. This is the messy reality of exoplanet science. Detections are rarely clean. Data is rarely unambiguous. Every method has limitations, every instrument has biases, and teasing out the truth requires combining multiple observations, multiple techniques, multiple independent confirmations. Webb added a piece to the puzzle of Alpha Centauri b's possible planet, but that piece complicated the picture rather than simplifying it. And then there was Proxima Centauri. Proxima is the third member of the Alpha Centauri system, the red dwarf orbiting the binary pair at a distance of about 13,000 astronomical units. It's the closest star to our Sun, slightly nearer than Alpha Centauri A and B, sitting just over 4 light years away. Proxima is tiny, about an eighth the mass of the Sun, and extraordinarily dim. In visible light, you need a telescope to see it at all, but in infrared, Proxima glows more brightly, and it's known to have at least 2 planets. Proxima Centauri b, discovered in 2016, orbits in the star's habitable zone, the region where temperatures might allow liquid water. It's about Earth mass, maybe slightly larger, and it completes an orbit every 11 days. That proximity to the star, that tight orbit, is necessary because Proxima is so dim. The habitable zone around a red dwarf sits much closer than it does around a sun-like star, but that closeness brings problems. Red dwarfs are active, prone to flares, massive eruptions of energy that can strip away planetary atmospheres, sterilize surfaces, make life difficult or impossible even in the so-called habitable zone. Proxima Centauri b is one of the most studied exoplanets precisely because it's so close. Astronomers have used every available technique to learn more about it. Radial velocity measurements confirmed its mass. Transit observations tried to see if it passes in front of its star from our perspective, which would allow measurements of its atmosphere. But so far, those observations have been inconclusive. The planet might not transit, or it might, and we just haven't caught it at the right time with the right instruments. James Webb observed Proxima Centauri as part of its Alpha Centauri program. The goal was to look for atmospheric signatures from Proxima b to see if the planet had retained an atmosphere despite the star's flares, and if so, what that atmosphere was made of. The observation required exquisite timing, catching the planet during a transit if transits occur, or during certain phases of its orbit, when the planet's thermal emission would be most distinguishable from the stars. Webb observed. The data came back, and once again, the results were ambiguous. There were hints of something, variations in the infrared signal that might indicate an atmosphere, but the variations were small, within the noise margins, difficult to interpret. Some scientists thought they saw evidence of carbon dioxide, a common atmospheric component that absorbs and emits infrared light at specific wavelengths. Others argued the signal could be explained by the star itself, by variations in Proxima's brightness or temperature that mimicked an atmospheric signature. The observations didn't prove Proxima b has an atmosphere. They didn't prove it doesn't. They added data points, narrowed probabilities, gave future scientists more to work with, but they didn't deliver the clear answer everyone wanted. This pattern repeated across all of Webb's Alpha Centauri observations. Every target, every measurement, every analysis yielded information but not certainty, and slowly, the astronomical community began to process what that meant. The closest star system, observed by the most powerful telescope ever built, still guarded its secrets, still refused to fully reveal itself. The realization was sobering. If we can't definitively characterize planets around stars 4 light years away, what does that say about our ability to find life elsewhere? What does it say about the search for Earth-like worlds, for biosignatures, for evidence that we're not alone? The targets that excite people, that drive funding and public interest, are habitable planets, worlds where life might exist. But finding those worlds, confirming they're habitable, detecting signs of life if it's there, all of that is vastly harder than most people realize. Finding a planet is step 1. Measuring its size and mass is step 2. Determining its atmosphere is step 3. Looking for biosignatures, oxygen, methane, combinations of gases that suggest biological processes, is step 4. Each step is harder than the last. Each step requires better instruments, longer observations, more sophisticated analysis, and even with James Webb, even with the best technology we have, we're still struggling with step 3 for the nearest planets. This doesn't mean the search is futile. It means the search is harder than the optimistic projections suggested. It means that when you read headlines claiming habitable worlds or potential signs of life, you should read carefully, look at the caveats, understand what the scientists actually measured versus what the headline implies. Detection is not confirmation. A planet in the habitable zone is not a habitable planet. A chemical signature that could be biological might also be geological or chemical, or an artifact of how starlight passes through an atmosphere. Webb's observations of Alpha Centauri drove this point home. They showed that even when everything is in our favor, nearby stars, powerful telescope, dedicated observation time, the universe doesn't give up its answers easily. Let's consider what easily would look like. Imagine an alternate reality where Alpha Centauri A has an Earth-sized planet orbiting at 1 astronomical unit, the same distance Earth orbits the Sun. Imagine this planet has an atmosphere rich in oxygen and methane, chemicals that don't naturally coexist unless something, probably life, is constantly producing them. Imagine this planet transits its star from our perspective, passing directly between us and Alpha Centauri A every year, blocking a tiny fraction of the star's light. In that scenario, James Webb could observe multiple transits. It could measure how the starlight changes as it filters through the planet's atmosphere. Different molecules absorb light at different wavelengths, creating a spectral fingerprint that reveals the atmosphere's composition. With enough transits, enough data, Webb could detect oxygen, methane, water vapor, carbon dioxide. It could build a chemical profile of the atmosphere. And if that profile showed the oxygen-methane combination, along with other supporting evidence, scientists could make a tentative, heavily caveated claim about possible biosignatures. That's the dream scenario. That's what exoplanet science is designed to achieve, but it requires everything to align. The planet has to exist. It has to transit. It has to have a thick enough atmosphere to produce detectable signals. The star has to be quiet enough that its own variability doesn't overwhelm the atmospheric features. The observations have to be timed perfectly, repeated multiple times, processed carefully to remove noise and artifacts. At Alpha Centauri, nothing aligned. The planets, if they exist, don't clearly transit. Their atmospheres, if they have them, are too faint to detect with current methods. The stars, particularly Proxima, are active and variable, complicating every measurement, and so the dream scenario remains a dream. The reality is uncertainty, constraint, gradual progress. But there's value in that reality, even if it's not satisfying. Constraints tell you where to look next. They tell you what kinds of observations might help, what instruments you need, what questions are answerable and which aren't. Before Webb observed Alpha Centauri, the range of plausible planetary systems was huge. Now it's smaller. Still large, still frustratingly uncertain, but smaller. And each new observation will shrink it further. There's another dimension to the Webb observations that didn't make it into most of the scientific papers, but mattered deeply to the researchers involved. It's the emotional dimension, the psychological weight of studying something so close and yet so unreachable. Astronomers are human. They have the same curiosity, the same desire for discovery, the same frustration with ambiguity that everyone does. When you spend years preparing an observation proposal, arguing for telescope time, waiting for your data, and then months analyzing what comes back, you develop a relationship with your target. You think about it constantly. You dream about what you might find. You run through scenarios in your head, imagining the paper you'll write, the announcement you'll make, the small mark you'll leave on human knowledge. And when the data comes back ambiguous, when it doesn't answer the question you hoped it would, there's a very real sense of disappointment. Not because you failed. You did everything right. The observation was successful. The data is good. But because the universe didn't cooperate. Because reality is messier than you wanted it to be. Several scientists involved in the Alpha Centauri observations have spoken about this, usually in informal settings, over coffee at conferences or in late-night conversations after symposia. They talk about the weight of proximity, the burden of knowing that the answers they seek are right there, 4 light years away, close enough to feel tangible, but still completely inaccessible. They talk about looking at the data and seeing hints, suggestions, maybes, and wanting so badly to turn those into certainties. They talk about the discipline required to stay honest, to not overinterpret, to not see planets in noise because you want planets to be there. This is the human side of astronomy, the part that doesn't appear in journal articles or press releases, the part where scientists struggle with the same cognitive biases everyone does, the tendency to see patterns where none exist, to inflate the significance of weak signals because they fit the narrative you hope is true. Good scientists develop tools to fight those biases, blind analysis, where you don't look at the final results until all processing decisions are made, statistical tests that quantify how likely a signal is to be real versus random, peer review, where other scientists scrutinize your work and point out the flaws you missed. But those tools don't eliminate the emotional experience. They don't remove the disappointment when your carefully planned observation doesn't deliver a clear result. And they don't resolve the deeper frustration of knowing that the question you're asking, are there planets like Earth around the nearest stars, might not be answerable with current technology, that you might spend your entire career building toward observations that will forever remain just shy of definitive. This frustration doesn't mean scientists give up. It means they recalibrate. They adjust their questions. Instead of asking, are there habitable planets around Alpha Centauri? They ask, what can we rule out? What constraints can we establish? What future observations would help? They shift from seeking discovery to building foundations, from trying to answer the big question to answering the smaller questions that might eventually lead to the big answer. It's slower, it's less glamorous, it doesn't generate headlines, but it's how science actually progresses. James Webb's observations of Alpha Centauri fit into a broader pattern in modern astronomy, a shift from discovery-driven science to constraint-driven science. For most of human history, astronomy was about finding new things. New stars, new planets, new galaxies, new phenomena. The field advanced through discovery, through pointing telescopes at unexplored regions and seeing what was there. That approach worked because the universe was largely unknown. Almost anywhere you looked, you found something new. But we've entered a different era. We've mapped the sky. We know where the stars are, where the galaxies are, what the large-scale structure of the universe looks like. There are still discoveries to be made, still objects we haven't seen, still phenomena we don't understand. But increasingly, the questions astronomers ask aren't, what's there, but what are the properties? What are the processes? What are the limits? This shift changes how we design observations, how we interpret data, how we define success. A null result, looking for something and not finding it, is no longer a failure. It's information. It tells you that whatever you were looking for is either absent or fainter than your detection threshold. That's useful. It constrains theories, eliminates possibilities, focuses future searches. Webb's Alpha Centauri observations produced several null results. No clear detection of planets, no obvious atmospheric signatures, no large dust structures. Each null result narrowed the space of possibilities. Each one told scientists something about what Alpha Centauri isn't, even if it didn't reveal what Alpha Centauri is. In the papers published from those observations, you can see this philosophy at work. The abstracts don't claim discoveries, they report limits. We constrain the presence of planets larger than X-Earth masses in orbits between Y and Z astronomical units. We detect warm dust with temperatures consistent with distances of A to BAU from the primary star. We find no evidence for atmospheric features on Proxima b, above our detection threshold of C parts per million, to a general audience. This language sounds weak, uncertain, unexciting, but to scientists, it's gold. Those constraints can be fed into models. They can guide the design of future telescopes. They can inform decisions about where to point instruments, what targets are worth pursuing, what questions are answerable. This is the legacy of Webb's Alpha Centauri observations. Not a breakthrough, but a foundation. A set of measurements that future astronomers will build on, compare to, improve upon. In 10 years, when the next generation of telescopes comes online, larger ground-based observatories, potential space missions designed specifically for exoplanet imaging, scientists will return to the Webb data. They'll use it as a baseline, a reference point, a comparison. They'll combine it with new observations to extract insights neither dataset could provide alone. And maybe, eventually, the combination of Webb's data and future data will answer the question everyone wants answered. Maybe we'll confirm an Earth-like planet in Alpha Centauri's habitable zone. Or maybe we'll conclusively rule it out, demonstrate that no such planets exist, and redirect our attention to other nearby stars. Either outcome would be valuable. Either outcome would advance our understanding, but we're not there yet. We're still in the phase of accumulating constraints, building the foundation, waiting for the next piece of the puzzle. There's a concept in astronomy called the observational horizon, the boundary of what we can detect with current technology. That horizon shifts over time as instruments improve, but it's always there, always limiting what we can learn about the universe. For exoplanets around nearby stars, the observational horizon is frustratingly close to the questions we most want to answer. We can detect large planets easily. Jupiter-sized worlds stand out in radial velocity measurements because obvious transits are bright enough in infrared to image directly if they orbit far enough from their stars. We can detect medium planets with more effort. Neptune-sized worlds require more sensitive measurements, longer observation times, more careful data analysis, and we can barely detect small planets, Earth-sized and smaller, and only under ideal conditions. The problem is that the planets we care most about, the ones that might harbor life, are small. They're rocky. They orbit in habitable zones, at moderate distances from their stars. They're exactly the planets that sit at, or beyond our observational horizon. We know they exist. Surveys suggest that most Sun-like stars have at least one rocky planet in or near the habitable zone, but detecting them individually, confirming their properties, characterizing their atmospheres, all of that requires pushing instruments to their limits. Alpha Centauri sits right on that boundary. The system is close enough that we should be able to see planets if they're there, but should doesn't mean can. The planets that might exist, the Earth-sized worlds in habitable zones, are at the very edge of detectability. Some observation methods work, some don't, and the ones that work require perfect conditions, multiple measurements, years of effort. James Webb extended our observational horizon slightly. Its infrared sensitivity, its stability, its coronagraphic capabilities, all of those pushed the boundary of what we can see, but they didn't push it far enough to definitively answer the question of habitable planets around Alpha Centauri. They brought us closer, gave us better constraints, but didn't cross the threshold from uncertainty to knowledge. That threshold crossing will require more. Better coronagraphs that can block starlight more effectively, larger mirrors that collect more light, improving sensitivity, longer observation times that allow for statistical certainty, or entirely new techniques, methods that don't rely on direct imaging or transit observations, approaches we haven't invented yet. Some of those improvements are already in development. The next generation of ground-based telescopes, the extremely large telescopes currently under construction, will have mirrors 30 to 40 meters across. Compared to Webb's 6.5 meter mirror, they'll observe invisible and infrared light using adaptive optics to correct for atmospheric turbulence, achieving resolutions that rival or exceed Webb's. They'll have advanced coronagraphs, instruments specifically designed to image exoplanets around nearby stars. Alpha Centauri is a target for those telescopes. Observation programs are already being planned. Simulations run to predict what might be detectable. If there are Earth-sized planets in the habitable zones, if those planets have atmospheres, the extremely large telescopes should see them. Not easily, not quickly, but eventually with enough observation time and careful enough analysis. There are also proposals for space missions dedicated to exoplanet imaging. Concepts like HABEX, the Habitable Exoplanet Observatory, or LAVIOIR, the Large UV Optical IR Surveyor, both studied extensively by NASA, but not yet funded or approved. These missions would use much larger mirrors than Webb, along with starshades or advanced coronagraphs, to directly image Earth, like planets, and characterize their atmospheres. Alpha Centauri would be a prime target, possibly the first system observed. But these missions are expensive, complex, and years away. HABEX and LAVIOIR, if funded, wouldn't launch until the late 2030s or 2040s. The extremely large telescopes will come online sooner, in the late 2020s or early 2030s, but they face their own challenges, technical hurdles that could delay operations or limit performance. So we wait. We use the instruments we have now, like Webb, to gather what data we can. We publish constraints, refine models, prepare for the next generation. We accept that some questions won't be answered in our lifetimes, that the search for life around other stars is a multi-generational project, one that will unfold over decades and centuries, with each generation contributing a small piece to the larger puzzle. This long timescale frustrates people. We live in an era of instant information, where answers are supposed to be a search query away, where waiting feels like failure. But astronomy doesn't work on human timescales. The universe doesn't care about our impatience. Stars evolve over billions of years. Light takes years to cross even the nearest interstellar distances. Building telescopes, launching missions, analyzing data, all of that takes time. Progress happens, but slowly, incrementally, in steps so small they're only visible in retrospect. Webb's observations of Alpha Centauri are one small step, a contribution to a process that started before Webb launched and will continue long after it ceases operation. The telescope has a finite lifespan, determined by how much propellant it has to maintain its position and orientation. Current estimates suggest Webb will function for at least 20 years, possibly longer if its systems remain healthy. During that time, it will observe thousands of targets, collect unimaginable amounts of data, contribute to discoveries we can't yet predict. But it won't answer every question. It won't find definitive proof of life around other stars. It won't image Earth, like planets around Alpha Centauri, with enough detail to see continents and oceans. Those achievements, if they're possible at all, will require instruments that don't exist yet, technologies we haven't developed, investments we haven't made. And that's okay. Science is not a sprint. It's a relay race, with each generation passing the baton to the next. Webb is one runner in that race, carrying the baton farther than its predecessors could, setting up future runners for their leg of the journey. One of the questions that came up repeatedly in discussions about Webb's Alpha Centauri observations is whether the effort was worth it. Telescope time is precious. Webb is oversubscribed, with far more observation proposals submitted than time available. Every hour spent observing Alpha Centauri is an hour not spent on something else, some other scientific question, some other target. Given that the observations didn't produce clear detections, didn't definitively answer whether habitable planets exist in the system, was it the right decision to observe Alpha Centauri at all? The scientists involved argue yes emphatically. Even null results are results. Even constraints are valuable. And there's an argument that Alpha Centauri deserves special attention precisely because it's the nearest star system, because it represents our best chance of detailed study, because if we ever send a mission to another star, it will almost certainly go there. But there's also a counter-argument. With limited resources, should we focus on targets where we're more likely to get clear answers? There are other nearby stars, some with already confirmed planets. There are transiting exoplanets where atmospheric measurements are easier. There are distant galaxies, star-forming regions, targets that might yield more dramatic results, more publishable findings, more public excitement. This tension between what's scientifically important and what's practically achievable runs through all of astronomy. Every observation proposal is a bet, a wager that the time and resources invested will pay off in new knowledge. Some bets win, some don't, and often you don't know which is which until after the data is collected and analyzed. Alpha Centauri is a long-term bet, a decision that maybe this observation won't give clear answers, but it will contribute to a body of work that eventually does. It's infrastructure, not breakthrough. Foundation, not finished building. And viewed that way, Webb's observations succeed. They added data points. They constrained possibilities. They demonstrated what's detectable and what isn't. They set benchmarks for future instruments. They forced scientists to refine their models, to think harder about dust distribution and thermal emission and the limitations of coronagraphy. All of that has value, even if it doesn't make headlines. There's a particular moment in the analysis of Webb's Alpha Centauri data that captures the essence of modern astronomy's relationship with ambiguity. A researcher, working late in their office, was examining the thermal maps of the system, looking at the distribution of warm dust around Alpha Centauri A. The data showed a concentration of material at roughly the right distance for a planet's orbit, a warm spot that could be explained by a planet shepherding dust, its gravity creating a resonance that concentrated particles in a particular region. The researcher ran simulations, testing whether a planet could produce the observed pattern. The answer was yes. An Earth-sized planet in that orbit would create exactly that kind of concentration. The thermal signature matched. The location made sense. Everything fit. But simulations also showed that other explanations fit just as well. A clump of dust with no planet. A temporary concentration created by a recent collision between asteroids. An artifact of how the starlight scattered, creating an illusion of warmth where none truly existed. The researcher looked at the data, looked at the simulations, and realized there was no way to know which explanation was correct. Not from this data alone. Not without additional observations, different wavelengths, different angles, different techniques. The planet might be there, the planet might not. The data allowed both possibilities. In the end, the researcher wrote up the analysis, presented all the explanations, and concluded that the observations were consistent with but do not require the presence of a planet. It's careful language, honest language, the kind of language that acknowledges uncertainty rather than hiding it. That moment, that decision to be honest about ambiguity rather than claiming more certainty than the data supports, is what separates good science from wishful thinking. It's not satisfying. It doesn't give the public the clear answers they want, but it's truthful. And in science, truth matters more than satisfaction. The public's relationship with scientific uncertainty is complicated. People want answers. They want to know if there are planets around Alpha Centauri, if those planets are habitable, if they might harbor life. They don't want caveats and confidence intervals and statements about detection thresholds. They want yes or no, definitive, clear. But reality doesn't offer that clarity, especially at the frontiers of knowledge. At the edge of what we can observe, what we can measure, what we can infer, everything is fuzzy. Everything is probabilistic. Everything comes with error bars. Scientists understand this. They're trained to think in probabilities, to be comfortable with uncertainty, to update their beliefs as new evidence arrives. But communicating that uncertainty to the public is hard. Say, we found hints of a possible planet, and some people hear, we found a planet. Say, we can't rule out the presence of a planet, and others hear, there's definitely no planet. The nuance gets lost. The careful hedging gets flattened into a binary. This communication challenge affects how scientists talk about their findings. Some err on the side of caution, downplaying their results to avoid overstating the case. Others emphasize the exciting possibilities, the hints and suggestions, hoping to generate public interest and support for future observations. Neither approach is wrong, but they create different impressions, different narratives, different levels of public excitement or disappointment. With Alpha Centauri, most scientists have leaned toward caution. They've emphasized the constraints, the limits, the need for more data. They've avoided claiming detections when the evidence is weak, and as a result, the public perception is that Webb didn't find anything at Alpha Centauri, that the observations were somehow a failure or disappointment. But that perception misses the point. Webb found a lot. It found dust configurations that don't match simple models. It found thermal signatures that need explaining. It found limits on planetary sizes and orbits. It found evidence for stellar activity around Proxima. It found data that will keep scientists busy for years, analyzing, modeling, arguing over interpretations. What it didn't find is easy answers, simple confirmation of what we hoped was true. And maybe that's the real lesson of the observations, that the universe doesn't organize itself around our hopes, that proximity doesn't guarantee accessibility, that even with the best tools we've ever built, some questions remain stubbornly out of reach. There's something almost philosophical about Alpha Centauri's resistance to revelation. It sits there in the sky, close enough to see with unaided eyes, bright enough to be familiar, and yet it refuses to give up its secrets. Every observation brings new information, but not resolution. Every measurement narrows possibilities, but doesn't eliminate uncertainty. The system exists in a quantum state of astronomical knowledge, where planets both do and don't exist until some future observation forces reality to choose. That metaphor isn't quite right, of course. Reality has already chosen. The planets either exist or they don't. What's quantum is our knowledge, our observation, the state of not yet knowing collapsing only when we gain enough information to be certain. But when will we gain that information? When will the uncertainty resolve? The honest answer is we don't know. Maybe the next generation of telescopes will do it. Maybe it will require the generation after that. Maybe it will take a probe, an actual mission to Alpha Centauri, to definitively map the system and confirm what's there. Or maybe we'll never be completely certain, never fully resolve every question, because the universe is vast and complicated and finite resources mean some mysteries remain forever unsolved. That possibility bothers people. The idea that we might never know if there are habitable planets around the nearest stars, never confirm whether life exists elsewhere, never get the clear answer to humanity's oldest question, are we alone? It feels like failure, like all this effort, all these telescopes and missions and centuries of observation should eventually pay off with certainty. But maybe that expectation is wrong. Maybe the universe isn't obligated to provide easy answers. Maybe some questions are too hard, too distant, too entangled with the limits of what's physically possible to ever fully resolve. And maybe learning to live with that uncertainty, to continue searching even knowing we might never find, is part of what it means to be a scientific civilization. James Webb's observations of Alpha Centauri fit into this larger narrative. They're a chapter in an ongoing story, a story that started when humans first looked up at the stars and wondered what they were, and that will continue as long as humans exist and remain curious. Webb added to that story. It contributed data, insights, constraints. It moved the narrative forward, even if it didn't reach a conclusion. And in the end, that's what we should expect from astronomy. Not closure, but progress. Not answers, but better questions. Not certainty, but narrowing uncertainty, degree by degree, observation by observation, until maybe, someday, we know enough to say we understand. The final papers from Webb's Alpha Centauri observations were published across 2023 and 2024, appearing in journals like Nature Astronomy, the Astrophysical Journal, and Astronomy and Astrophysics. They total thousands of pages of analysis, figures, tables, models. They represent years of work by hundreds of scientists, all focused on a few dozen hours of observation time. A few datasets collected by a telescope orbiting 1 million miles from Earth. Reading through those papers, you see the scientific process laid bare, the careful methodology, the statistical rigor, the honest acknowledgement of limitations, the detailed discussion of alternative interpretations, the conclusions that hedge and qualify, that avoid overstatement, that resist the temptation to claim more than the data supports. You also see passion in the way the papers are written, in the attention to detail, in the thoroughness of the analysis. These scientists care deeply about Alpha Centauri, about exoplanets, about the search for life. That care drives them to be meticulous, to check and double check, to consider every possible explanation before settling on the most likely one. And you see hope that future observations will clarify what these observations couldn't. Hope that the constraints they've established will guide those future observations, making them more efficient, more targeted. Hope that this work, this contribution to the slow accumulation of knowledge, will matter in the long run. That hope is justified. Science builds. Every observation adds to the foundation. Every constraint narrows the search space. Every null result eliminates a possibility and points toward more promising directions. It's slow, it's frustrating, but it works. Over time, with enough effort, with enough people contributing their small pieces, the picture clarifies. We're not there yet with Alpha Centauri. We don't know if habitable planets exist in the system. We don't know if life has emerged elsewhere, even in the nearest stars. We don't know if we're alone. But we know more than we did before Webb observed. We know the dust distribution. We know the thermal environment. We know the limits on planetary sizes. We know what future observations need to target, what techniques might work, what questions are answerable. That's progress. Slow, incremental, unglamorous progress, but progress nonetheless. And perhaps that's the real shock that James Webb delivered when it looked toward Alpha Centauri. Not a discovery, not a breakthrough, but a revelation about the nature of scientific progress itself, about how hard one knowledge really is, about how the universe guards its secrets even when we build ever more sophisticated tools to extract them. The shock is that proximity doesn't guarantee understanding. That forelight, years might as well be 4,000 when it comes to the questions we most want answered. That the best telescope humanity has ever built, pointed at the nearest star system, still can't give us certainty. That's sobering. It's humbling. It forces us to recalibrate our expectations, to accept that some questions might take centuries to answer, to recognize that the search for life elsewhere is genuinely hard, not because we're doing it wrong, but because the universe makes it hard. But it's also inspiring, because despite the difficulty, despite the ambiguity, despite knowing that clear answers might never come, scientists keep looking. They keep proposing observations. They keep analyzing data. They keep publishing constraints and limits and incremental findings. They keep contributing to a project that spans generations, that no single person will see completed, but that collectively moves humanity forward. That persistence in the face of uncertainty, that commitment to the search even knowing it might never conclude, says something profound about human nature. We're curious, we want to know, and we're willing to accept partial answers, probabilistic results, slow progress, because partial answers are better than no answers, because the search itself has value, because not knowing but trying to find out is better than not knowing and giving up. James Webb's observations of Alpha Centauri embody that spirit. They didn't give us the answers we wanted. They gave us what was possible to learn with the tools we have at the moment we asked, and they set the stage for the next question, the next observation, the next small step toward understanding. The scientists who worked on those observations know their papers will be cited for years, that future researchers will build on their findings, that the constraints they established will shape how we think about nearby stars and exoplanets. They know their contribution matters, even if it's not the final word, and they know that somewhere, maybe decades from now, maybe centuries, another telescope will observe Alpha Centauri, better instruments, different techniques, more sensitive detectors, and that telescope will add to what Webb found, will narrow the uncertainties further, will bring us closer to knowing what exists in the nearest star system. Whether we'll ever know for certain, whether the question will ever be fully answered, remains uncertain. But the search continues, the observations accumulate, the knowledge grows slowly, piece by piece, and Alpha Centauri waits 4 light years away, keeping its secrets a little while longer. There's a timeline that astronomers sometimes construct, a rough projection of when we might expect certain capabilities, certain observations, certain answers. It goes something like this: late 2020s, extremely large telescopes come online. First direct imaging of potentially habitable planets around nearest stars, including possibly Alpha Centauri. Atmospheric characterization begins for brightest targets. Early 2030s, enhanced space telescopes or missions launch. Improved sensitivity for exoplanet atmospheres. Better constraints on biosignatures. Mid-2030s, possible starshade mission or advanced chronograph mission. direct imaging of Earth-sized planets in habitable zones becomes routine for nearest stars. 2T40s and beyond, multi-decade observation campaigns compile enough data to make strong claims about habitability and potential biosignatures around nearest stars. It's a conservative timeline. It assumes current technology development continues at its present pace, that funding remains available, that no major breakthroughs accelerate progress, and no catastrophic failures delay it. It's also optimistic in assuming that the planets we want to find actually exist, that they're detectable with foreseeable technology, that nature cooperates with our search. But even this timeline means waiting another decade for meaningful new data on Alpha Centauri, waiting another 2 decades for definitive atmospheric characterization, waiting a lifetime for the kind of certainty that might let us say, with confidence, whether life exists in the nearest star systems. For the scientists working on these questions now, many in the prime of their careers, this timeline means they might not see the answer. They'll contribute data analysis, models, but the final confirmation or refutation might come after they've retired, after they've passed away, after their contributions have been built upon by others. There's something poignant about that, about dedicating your career to a question you know you might never see answered, about working toward a goal that extends beyond your lifetime. It requires a particular kind of faith, not religious faith, but faith that the work matters, that contributions add up, that the collective endeavor of science will eventually arrive at truth, even if individual scientists don't live to see it. That faith sustains the field. It drives people to spend years developing observation proposals, analyzing data, publishing findings that might seem incremental, but that fit into a larger mosaic, and it creates a sense of connection across time, a feeling that you're part of something bigger, something that started before you arrived and will continue after you leave. Webb's observations of Alpha Centauri are part of that continuum. The scientists who planned those observations built on work done by previous generations, astronomers who first measured the distance to Alpha Centauri, researchers who characterized the stellar properties, teams who search for planets using radial velocity and astrometry. Every generation added their piece, and now Webb has added its piece, data that will be used by the next generation. The astronomers who will design observations for the extremely large telescopes, who will propose missions for the 2030s and 2040s, who will be the ones to potentially find definitive evidence of planets, atmospheres, maybe even biosignatures around Alpha Centauri. Those future astronomers will look back at Webb's data the way current astronomers look back at observations from Hubble, from ground-based telescopes, from the earliest attempts to detect exoplanets. They'll see the limitations, the things Webb couldn't do, but they'll also see the contribution, the foundation that was laid, the questions that were sharpened and refined, and they'll be grateful for it. Science is collaborative not just across space, with researchers at different institutions working together, but across time, with each generation enabling the next. Webb's Alpha Centauri observations exemplify that temporal collaboration. They took what previous observations established and pushed it further, and they set up future observations to push further still. This long view, this multi-generational perspective, changes how you think about success and failure. A single observation that doesn't answer the big question isn't a failure. It's a step, a contribution, a piece of the puzzle. And enough steps, enough contributions, enough pieces eventually complete the picture. We're not there yet. The picture of Alpha Centauri remains incomplete, but it's less incomplete than it was, and that's worth something. As the scientific analysis of Webb's observations continued through 2024 and into 2025, certain patterns emerged from the data that weren't immediately obvious in the initial papers. One pattern involved the dust temperature distribution. The original analysis noted that some dust appeared warmer than expected for its distance from the stars, but assumed this was a minor complication, perhaps explained by grain composition or size distribution. But as more scientists examined the data, as more models were run, a different interpretation emerged. The warm dust might not be anomalous. It might be exactly what you'd expect if there were planets in the system, planets that hadn't formed recently, but billions of years ago, and that had since settled into stable orbits, their gravitational influence creating zones where dust accumulated and was heated by multiple sources, direct starlight, reflected light from the planets themselves, and resonant interactions that concentrated energy in unexpected ways. This interpretation didn't prove planets existed. It just made them more likely. shifted the probabilities slightly in favor of planetary systems that matched the thermal signature, and importantly, it made testable predictions. If this model was correct, if planets were shepherding the dust, then observations at different wavelengths should show corresponding patterns. Different dust grains emit differently depending on their size and temperature, so measuring the spectrum across a wider range should reveal whether the warm dust was a single population or multiple populations, each with different characteristics. Those follow-up observations haven't been done yet. They're proposed, scheduled for future Webb observation cycles, but they haven't happened, so the interpretation remains speculative, a possibility supported by the data, but not confirmed by it. This is typical of how astronomy progresses. An observation raises questions. Models are developed to explain the observation. Those models make predictions. New observations test the predictions. The cycle repeats, each iteration refining understanding, narrowing possibilities. We're in the middle of that cycle with Alpha Centauri. The first iteration, Webb's initial observations, is complete. The models are being developed, the predictions are being made, and the next iteration, follow-up observations to test those predictions, is being planned. How many iterations will it take to definitively answer whether habitable planets exist around Alpha Centauri? No one knows. Maybe the next observation will do it. Maybe it will take 10 more. Maybe it will take 50, spanning decades, requiring instruments that don't exist yet. But each iteration brings us closer. Each one eliminates some possibilities and strengthens others. Each one adds to the collective knowledge, the shared understanding built across research groups, across nations, across generations. And in the meantime, while we wait for those future observations, scientists continue mining the existing data, looking for patterns others missed, testing alternative models, pushing the analysis to its limits to extract every possible insight. Because that's what you do with precious data. You don't analyze it once and move on. You return to it repeatedly, asking new questions, applying new techniques, seeing if there's more to learn. Webb's Alpha Centauri observations will be analyzed for years, possibly decades. Each analysis might reveal something new, some subtle feature that previous analyses overlooked, some correlation that becomes apparent only when you combine the data with information from other sources. This iterative, long-term approach to data analysis is part of what makes modern astronomy so powerful. It's not just about collecting data, it's about extracting meaning from that data, and that extraction is often a slow, painstaking process that requires creativity, patience, and willingness to reconsider conclusions when new evidence or methods suggest a different interpretation. The scientists working on Alpha Centauri understand this. They know the papers they've published aren't final words. They're progress reports, snapshots of understanding at a particular moment. As techniques improve, as computational power increases, as new theoretical models are developed, those papers will be revisited, refined, possibly overturned. And that's healthy. That's how science should work. Tentative conclusions, always subject to revision, always open to challenge. It's the opposite of dogma, the opposite of claiming certainty where none exists. What James Webb revealed, more than any specific finding about Alpha Centauri, is the persistence of uncertainty at the frontiers of knowledge. Even with revolutionary instruments, even with observations of the nearest stars, we remain in a state of not knowing, of educated guessing, of probabilistic reasoning that acknowledges multiple possibilities. That uncertainty is uncomfortable. Humans don't like not knowing. We like clear categories, definite answers, resolution. The idea that we might study something intensely, with the best tools available, and still not know whether planets exist there, whether life might have emerged, whether we're looking at a future destination or a sterile system, that idea frustrates us. But astronomy requires accepting that frustration. It requires developing comfort with uncertainty, with probability, with the slow accumulation of evidence that shifts likelihood without providing proof. It requires recognizing that "we don't know yet" is a legitimate answer, possibly the most honest answer, and that continuing to search despite not knowing is valuable. This mindset doesn't come naturally. It has to be learned, practiced, reinforced through training and culture. And even scientists sometimes struggle with it, sometimes feel the pull toward claiming more certainty than the data warrants, toward seeing patterns that aren't quite there, toward believing that the answer they hope for is the answer that exists. Good scientific culture fights that pull. Peer review, statistical rigor, replication, transparency. All of these practices exist to keep individual biases and hopes from distorting collective understanding. They're not perfect. They don't eliminate error or bias completely, but they reduce it. They catch it more often than not. They create an environment where honesty about uncertainty is valued more than false confidence. The papers on Webb's Alpha Centauri observations demonstrate that culture. They could have claimed detections. The data had features that could be interpreted as planets if you wanted to see planets. But the authors chose caution, chose honest uncertainty, chose to present the data and its limitations rather than overselling conclusions. That choice matters. It maintains trust, both within the scientific community and with the public. It shows that astronomy is self-correcting, that scientists police themselves, that the field values accuracy over excitement, and it sets a standard for future observations. When the next round of data comes in, when the extremely large telescopes observe Alpha Centauri, the researchers analyzing that data will look at how Webb's observations were handled and try to match that standard. They'll strive for the same honesty, the same rigor, the same willingness to say, "We don't know," when they don't. That's the legacy of Webb's Alpha Centauri observations. Not a discovery, but an example. A demonstration of how to handle ambiguous data responsibly, how to advance knowledge without claiming more than you've learned, how to contribute to a multi-generational project with integrity. Those may not be the headlines people want. They may not generate excitement or public interest, but they're the foundation on which reliable knowledge is built. Among the teams analyzing Webb's data, there's an ongoing debate about whether to propose additional observations. More time on Webb, different configurations, different wavelengths might resolve some of the ambiguities. But telescope time is limited and expensive, and there are strong arguments for observing other targets, systems where results might be clearer, where the science return per hour of observation might be higher. It's a resource allocation problem. Do you focus on the nearest star because it's the nearest, because it represents our best hope for future exploration, because the question of what's there matters deeply even if answering it is hard? Or do you diversify, observe multiple systems, maximize the likelihood of clear detections even if those detections are farther away, less personally meaningful? Different scientists come down differently on this question. Some argue passionately for continued Alpha Centauri observations, saying that we owe it to future generations to learn everything possible about the nearest star while we have the opportunity. Others argue just as passionately for breadth over depth, for observing many systems to build statistical understanding of exoplanet populations, rather than focusing on one system that might not be representative. Both arguments have merit. Both reflect legitimate scientific values, and the resolution will come down to committee decisions, proposal reviews, assessments of what's most likely to advance the field. But underlying the debate is a deeper question about the purpose of astronomy. Is it primarily about understanding the universe in general, about building comprehensive theories that explain how stars and planets and galaxies work? Or is it about understanding our specific cosmic neighborhood, about answering the questions that matter most directly to humanity's future? The honest answer is both. Astronomy serves multiple purposes, satisfies multiple curiosities, addresses questions at different scales, general and specific, theoretical and practical, distant and near. All of these are valid focuses, all contribute to the larger enterprise. But when resources are limited, when you have to choose, the decision becomes fraught, and Alpha Centauri sits at the intersection of that tension. It's a general astronomical object, one star system among billions. But it's also our neighbor, the nearest stellar system, the place we'd go first if we ever developed interstellar travel. That dual nature makes it simultaneously a priority and just another target, and how we choose to observe it, how much time and effort we invest, reflects our values as a civilization, our balance between pure knowledge and practical relevance. Webb's observations represented one choice in that ongoing balance. The time was allocated, the observations were made, the data was collected, and now we live with the results, building on what we learned, planning what comes next. There's no perfect answer to resource allocation, no objective measure of whether Alpha Centauri deserves more attention than other exoplanet targets. It's a judgment call, informed by science but also by values, priorities, visions of what matters most, and different people will judge differently. What's important is that the decision-making process is thoughtful, that it weighs alternatives carefully, that it considers both short-term returns and long-term significance. The committees reviewing observation proposals try to do this, try to balance competing interests and make decisions that serve the field as a whole. Sometimes they'll favor Alpha Centauri, sometimes they won't. And over time, across many decisions, a pattern will emerge that reflects the community's collective priorities. That's how science self-organizes, not through top-down mandates, but through distributed decisions, individual choices aggregating into a direction, a focus, an allocation of effort that no single person controls, but that emerges from the system as a whole. And within that system, Alpha Centauri will remain a draw, a target that keeps coming up, keeps getting proposed, keeps receiving attention because of its nearness, its significance, its hold on human imagination. Not every proposal will be accepted, not every observation will be funded, but over time, across multiple observatories, across multiple programs, Alpha Centauri will accumulate data, slowly, incrementally, each observation adding a piece, refining the picture, bringing us closer to understanding what's actually there. That's the trajectory we're on. Not a dramatic rush to discovery, but a patient accumulation of knowledge. Not a single breakthrough observation, but a long campaign spanning decades, possibly centuries, with each generation contributing what they can. It's not the story people want, but it might be the story we have. And if we're honest with ourselves, if we accept the reality of astronomical timescales and the difficulty of the questions we're asking, it's the story we should expect. Because the universe doesn't give up its secrets easily. It doesn't organize itself for our convenience. It simply exists, following its own laws, indifferent to our curiosity and our timelines. We're the ones who have to adapt. We're the ones who have to develop patience, build instruments, design observations, analyze data, publish findings, and pass the work to the next generation. And we're the ones who have to find meaning in that process, satisfaction in the slow accumulation of knowledge, purpose in contributing to something larger than ourselves. James Webb's observations of Alpha Centauri are part of that larger something. They're part of humanity's ongoing effort to understand the cosmos, to map our place in it, to answer the ancient questions about whether we're alone and what else might be out there. The observations didn't answer those questions, but they advanced them. They moved the inquiry forward, provided data that will inform decades of future work, set constraints that will guide the next generation's observations. And in doing so, they fulfilled their purpose, not to solve the mystery, but to illuminate it, not to provide final answers, but to frame better questions. That's what this moment in astronomy represents, not the end of the search, but a waypoint, a marker showing how far we've come and how far we still have to go. We've built a telescope that can see the thermal glow of dust around the nearest stars. We've developed techniques to separate that glow from the stars themselves, to measure its spectrum, to model its sources. We've constrained the possible planetary systems, narrowed the range of what could exist, but we haven't seen Earth-like planets directly. We haven't confirmed atmospheres on rocky worlds in habitable zones. We haven't detected biosignatures, the chemical fingerprints that might indicate life. Those achievements remain ahead of us. Targets for future instruments, goals for the next decades, questions that will define careers and drive missions. And Alpha Centauri will remain central to that quest, because it's close, because it's reachable, at least in principle, even if the practice remains beyond current technology. Because if we're going to find life elsewhere, if we're going to confirm habitable worlds, if we're going to take the next step from detection to exploration, Alpha Centauri is where we'll likely start. So we keep looking, keep observing, keep analyzing, keep building better instruments and refining our techniques, not because we're certain to succeed, but because the question matters, because not knowing drives us, because the search itself, the process of reaching toward understanding, defines us as a curious, knowledge-seeking species. James Webb looked toward Alpha Centauri and saw dust, thermal signatures, stellar behavior, constraints. It saw what was possible to see with infrared eyes from 1 million miles away, looking across 4 years of distance at a system that's been shining longer than Earth has existed. It didn't see everything, it didn't answer every question, but it saw more than we could see before, and it set the stage for seeing more still. That's progress. Quiet, incremental, unglamorous progress, but progress nonetheless. And in a universe where distances are measured in light years, where answers take generations to find, where certainty comes slowly if it comes at all, quiet progress is what we have. It's what we've always had, and it's what we'll continue to build on, observation by observation, analysis by analysis, until someday, maybe, we know what exists in the nearest star system, or until we accept that some questions, despite our best efforts, remain beyond our reach. Either way, we'll have tried, we'll have looked, we'll have pushed the boundaries of knowledge as far as our technology and resources allowed. And that effort, that persistence in the face of uncertainty, might be the most human thing we do. The data sits in archives now, accessible to anyone with the credentials to access Webb's public database. Hundreds of files, gigabytes of measurements, the raw material of scientific understanding. Other researchers can download it, apply their own analysis techniques, test their own hypotheses. Some will find things the original teams missed. Some will argue with the published interpretations. Some will use the data to calibrate new instruments or validate new models. And all of that is part of the process, part of how science extracts maximum value from expensive observations. The cost of Webb's mission is measured in billions. Every observation represents a fraction of that investment. Making that investment pay off requires squeezing every possible insight from the data, which means not just analyzing it once, but repeatedly, from different angles with different methods, asking different questions. The Alpha Centauri data will be mined for years, probably decades. As long as people care about nearby stars and exoplanets, as long as the question of habitability and life remains compelling, researchers will return to this data, looking for clues others might have missed. And occasionally, someone will find something, a subtle correlation, an unexpected pattern, a feature that only becomes apparent when you combine Webb's data with observations from other telescopes, other wavelengths, other epochs. Those discoveries will lead to new papers, new analyses, new proposals for follow-up observations. The cycle continues, feeding on itself, each finding generating questions that require more data to answer. This is the long tail of a major observation. The immediate analysis, the first papers, those are just the beginning. The real value accrues over time, as the data becomes integrated into the broader knowledge base, as it's combined with other information, as it's reinterpreted in light of new theories and discoveries. Webb's Alpha Centauri observations have already begun that process. The data is public, the papers are published, the interpretation has started, but we're still in the early phase. The full impact, the complete understanding of what those observations revealed, won't be clear for years. That delayed gratification is another aspect of modern astronomy that challenges both scientists and the public. We want results now. We want to know immediately what an observation means, what it tells us, whether it's important. But importance often reveals itself slowly. An observation that seems routine might later prove crucial when combined with other data. A null result that seems disappointing might turn out to be the key constraint that eliminates a whole class of theories. You can't always judge the value of an observation at the moment it's made. You have to wait, see how it's used, see what it contributes to the larger understanding. With Webb's Alpha Centauri observations, we're in that waiting period. We know the immediate findings. We've read the first papers, but we don't yet know the full value, the complete contribution these observations will make. That will only become clear with time, as the data is integrated into the field's collective knowledge, as it shapes future observations and models, as it influences how we think about nearby stars and the search for habitable worlds. So we wait. And while we wait, we continue observing, continue analyzing, continue building toward the next piece of the puzzle, because that's what astronomy is, a long game, a multi-generational project, a slow accumulation of knowledge that doesn't respect individual timelines or career arcs or human desires for rapid resolution. The universe operates on its own schedule, and we have to match ourselves to that schedule if we want to understand it. James Webb gave us a glimpse of Alpha Centauri through infrared eyes. It showed us what 4 light years looks like when you filter out visible light and focus on heat. It revealed a system with dust, with stars of different sizes and temperatures, with complexity we're still working to understand, but it didn't give us closure. It didn't definitively answer whether habitable planets exist in the system. It didn't confirm or deny the possibility of life in the nearest stellar neighborhood. Those questions remain open, and they'll remain open until we build better instruments, make more observations, accumulate enough evidence to shift probability into certainty. How long will that take? We don't know. We can guess, project, estimate based on planned missions and telescope development timelines, but we can't know for sure. What we do know is that the search continues, that astronomers around the world are working on proposals, analyzing data, building instruments, doing the unglamorous work that advances the field incrementally. and that Alpha Centauri remains a focus, a target, a system that captures attention because of its nearness and its mystery. Webb looked, Webb measured, Webb constrained, and now Webb's data joins the archive, the accumulated knowledge, the foundation that future observations will build on. That's the legacy of the observations. Not dramatic discovery, but solid contribution. Not breakthrough, but foundation. And in science, foundation matters. Breakthroughs get attention, but they're built on foundation. They're made possible by the slow work that comes before, the observations and analyses that constrain possibilities and point toward productive directions. Webb's Alpha Centauri observations are part of that foundation. They'll support future discoveries, enable future breakthroughs, contribute to the eventual answer to the question of what exists in the nearest star system. When that answer comes, when we finally know whether Alpha Centauri hosts habitable worlds, whether life might exist just 4 light years away, Webb's observations will be part of the story, a chapter in the long narrative of discovery. Not the final chapter, not the climax, but a necessary part of the journey, a contribution that mattered, a piece that fit into the larger whole. And for the scientists who worked on those observations, who spent years planning and analyzing and writing, that's enough. That's the satisfaction they seek. Not glory, not headlines, but the knowledge that they contributed, that their work mattered, that they advanced human understanding even if just by inches. Because inches add up. Over time, across many contributions, inches become miles, and miles become understanding. That's the trajectory we're on with Alpha Centauri. Inch by inch, observation by observation, moving toward knowledge. We're not there yet, but we're closer than we were. And someday, maybe in our lifetimes, maybe in our children's or grandchildren's, we'll get there. We'll know what orbits those 3 stars. We'll know if any of those worlds could harbor life. We'll know whether the nearest stellar system is a destination or a curiosity. Until then, we keep looking, we keep measuring, we keep constraining and analyzing and building toward that eventual knowledge, because that's what we do. That's what curiosity demands. That's what it means to be a species that looks up at the stars and wonders. James Webb looked toward Alpha Centauri, and what it saw was both less and more than expected. Less certainty, fewer clear answers, more ambiguity than anyone hoped for. But also more data, more constraints, more foundation for future work. And in that balance, between disappointment and progress, between what we wanted and what we got, lies the reality of modern astronomy. It's hard, it's slow, it doesn't give easy answers, but it gives truth as much as we can discern it, and it gives direction, pointing toward the next observation, the next question, the next step forward. That's what Alpha Centauri represents now. Not a solved mystery, but an illuminated one. Not a finished story, but a continuing one. And we're part of it, watching from 4 light years away, waiting for the next piece of data, the next constraint, the next increment of understanding, waiting and looking and wondering what's really there.